Good morning, teenagers. This is Mr. Williams. It should be October the 1st, and this video is for my AP Physics 2 class. Today, we are going to be starting a new topic, but before we do, I want to remind you that yesterday we talked about the Carnot Cycle and heat engines. And I want to remind you to look back over that material. Wikipedia is actually really good in talking about the Carnot Cycle, C-A-R-N-O-T, the Carnot Cycle. There's adiabatic expansion and compression as you go between two isotherms. So remember, that involves adiabatic expansion and adiabatic compression as the system moves between two isotherms. I want to caution you that copying this down and memorizing this is not sufficient. You actually have to know all 4 steps in the Carnot cycle. You have to know what they mean, what's going on, how one leads to the other, and what is going on physically in a piston. If you don't know that, you should look up a YouTube video because we talked about this yesterday. So that's your responsibility. You need to know what the Carnot cycle is and what happens during the Carnot cycle in each of the 4 stages. That's the last bit of thermodynamics that I want to talk about with you. And so now it's time to move on to something that may be a little more pleasant. Let's talk about fluids. This is kind of where we started at the beginning of the year, but then we got kind of caught up in other discussions about temperature, and we backed up into thermodynamics. So here we are again, talking about fluids and density. I'm in chapter 13 of the night book. This is fluids. And we're going to start by talking about density. As I told you earlier in the year, the symbol for density is rho. That's rho. It looks like a P, but it isn't. So this is rho. Is the Greek symbol RHO. So you can just row your boat with that symbol. row your boat. Yes, bad jokes. That's where it's at. Bad jokes. Remember that this is rho and this is P. Well, that's rho is density and P is pressure. This is going to be a pain for you because I'm going to be using rho and P all together at the same time. So you have got to be able to tell from my terrible handwriting, for which I deeply regret it. I deeply apologize, but also I'm not changing it. So there you go. You've got to figure out from my terrible handwriting which is P and which is rho. And I'm trying. Rho's got this little tail on it and P doesn't. So there you go. So density is defined in the following fashion. Density is equal to the mass of an object divided by its volume. And we've had some long discussions already this year about volume, so you should be pretty good at 3-dimensional volumes. And if you're not, you need to practice. But hopefully you're good. If you look on page 399, table 13.1, you'll see some common densities there. Here they are. Holy macaroni, look how dense mercury is. Dense, oh my goodness, that is dense. 13,600 kilograms for every cubic meter. Wow. So a cubic meter is a meter this way and this way and this way. So that's a box that's a meter by a meter by a meter. That's pretty big. That's pretty big. A meter by meter by meter. So think about it. Look around the room, try to measure out in your own mind about how much a meter by meter by meter is. Okay, and remember a kilogram is, I don't know, about the mass of a good solid apple, a big heavy apple. So an apple, think about that as like a kilogram. And there is 13,600 apples in 1 cubic meter of mercury. That's pretty heavy. I wouldn't want to try to lift that. Let's think about seawater. I wouldn't want to carry a meter by meter by meter box of seawater either, and that's about 1,000 apples. That's still way too many for me. I don't think I could pick it up. Gasoline. Oh, look, gasoline isn't nearly as dense as water is. So gasoline is about 680 apples for 1 cubic meter. Okay. Air. Well, air actually has a weight. It's not just one. It has a weight, doesn't it? Look, air has a density. It's got 1.28 apples for every cubic meter of air. Okay, so there's actually stuff in the air. And you know that already because, like, if you wave your hand in the air, you can feel the air pressing back against you as you press forward. So you know that there's something in the air. There's a substance in the air. It turns out there's 1.28 kilograms of it every cubic meter. Look at helium. Look at helium. Oh, look. The temperature changes. As the temperature of air goes up, so it goes from 0 degrees Celsius to 20 degrees Celsius, then the density of air goes down. Oh, that should make sense from the last couple chapters when we were talking about the small particle nature of matter and how that applies to the ideal gas law. So as the gas, as its temperature goes up, it becomes less dense. Oh, well, yes, that's right. That's what we learned in the last couple chapters. Here it is right here, written down. 1.28 for 0 and 1.20 for 20. An inverse relationship. That's just awesome. Now look at this. Helium. Look how dense it is. It is very, very light per cubic meter. So it has a very, very low density. It's about, I don't know, maybe close to 20% of the density of air. So it's maybe a fifth as dense as air. All right. Hopefully that table has helped you to kind of ponder some of these interesting ideas. That's 13.1. Let's move on to 13.2. Liquids are essentially incompressible. No, they may not be. Maybe you can just compress them a little here or there, but for all practical purposes, in real life, liquids can't be compressed. And that's a very important point. Another important point is that liquids exert the same pressure everywhere at a particular depth. Let's look at this picture here on the notebook on page 400. If you have a container and it's got, I don't know, let's just say water. So it's got some water in here. Everywhere at a particular depth, the water is exerting a force out on the container with its exact same force. And if you were to punch a bunch of different holes in a glass of water, it would always press outward. The water's not like spurting straight up or I don't know, sideways upwards. It's shooting straight out, and then gravity pulls it down as it flies through the air. So, like it says here, it's important for you to realize that the force due to a fluid's pressure pushes not only on the walls of the container, but on all parts of the fluid itself. All parts. It is the force due to the pressure of the water behind each hole that pushes the water forward through the holes. There's a picture here. This is a little idea, a little thought experiment. We generally don't actually do this, but I suppose you could. You could imagine a little piston, like we talked about for the last 2 or 3 chapters, but instead of having a gas inside, you could have a little spring inside. And we learned about springs last year in AP Physics 1. You could imagine that you knew the spring constant to a fairly well. Like you actually went to the factory and you knew exactly what the spring constant was. Then, if you put this little piston inside the water, you could measure how hard the water was pushing in on the piston by how much compression occurred against the piston. And when you did that, you would find that no matter what depth you put your little measuring devices at, your pressure measuring devices, no matter what depth you put them in a fluid, everywhere at a particular depth, they would read the same exact pressure. Now, as you go down, the pressure increases. But at any particular height, like here or here or here, at any particular level, the pressure would be the same everywhere in that level. So there's some points here. I'm going to read them out to you. There is pressure everywhere in a fluid, not just at the bottom or at the walls of the container. The pressure at a given depth in a fluid is the same, whether you point the pressure measuring device up or down or sideways. And the fluid pushes up, down, and sideways with equal strength. In a liquid, the pressure increases rapidly with depth below the surface. This is not true for every substance because in a gas, the pressure is nearly the same at all points, at least in laboratory-sized containers. So there's a big difference between the gas and liquid. One of them is because the liquid is incompressible, it gets pulled down, but it can't compress. So that means that the weight of all the liquid above your measuring device is pressing down on the measuring device. So as you go deeper and deeper in the liquid, all the liquid above you is pushing down on you, on every part of you, so that the pressure increases dramatically as you go deeper and deeper into the liquid. And that is not the case with the gas. The pressure in the gas is going to be the same pretty much everywhere. This is a pretty good video. You might want to watch that at home. So use the QR code like we've done before in class and watch that video at home. Next, we're going to look at this little imaginary thing. If we want to measure the pressure that is felt down here, and we don't have a liquid measuring device like this with a little spring inside of a piston, well, then what the heck can we do? It's hard to imagine. So let's think about what we can do. Let's say that we have, you can imagine this dark little shape here is a cylinder of liquid. there's some caveats first. We have to assume that this liquid doesn't move. So this is a non-moving liquid. It's completely still. It's just sitting here, not flowing. We'll talk about flowing later in this chapter, but here it is, not flowing. And the liquid is, we're just going to look at this column of liquid. It's not actually in a tube or anything. We're imagining a column of liquid inside of our beaker. So here's this column of liquid. We want to know what the pressure is down here. Let's talk about the forces that are being exerted on the column. Well, there's the column has a depth D. We have the pressure of the air above our beaker pressing down, and that pressure would be the atmospheric pressure, P sub 0, multiplied by the cross-sectional area of our cylinder of water. We'd have the pressure going in at this side and the pressure going in at this side, but if it's at equilibrium, these two pressures are identical and they're going to cancel out. And then down here, we have the pressure exerted upwards of let's see. So remember I said earlier that everywhere in the liquid is pressing in all directions. So down here, the liquid at the bottom is pressing upwards. So the liquid at the bottom is pressing upwards with the pressure A. But up here, the atmosphere is pressing down with a pressure, I'm sorry, I said that wrong. Down here, the liquid is pressing upwards with the pressure P, not A. I don't know why I said A. Down here, the liquid is pressing upwards with the pressure P. And up at this end of the column, the air is pressing down with the pressure P sub 0 or P naught. I got distracted because the lights in this room went out for a second. I have to get up and walk around. That's what happens when you're making a video at 7:45 at night at the school. I have lost my mind. I could have just given you guys a worksheet, but I would not do that to you. So here I am, late at night, like a madman, making a video. All right, anyhow, whatever. We have the pressure of the air pushing down and the pressure of the liquid inside pushing up. Now, what other forces might there be? Well, the other force we might have is the mass of this column of water pushing down as well, or not pushing, I guess getting pulled by the earth. So this column of water has a mass, and the earth is pulling on it, and the force that the earth is pulling on it with is mg, because that's the weight of this column of water. So if we look at our little free body diagram, what's pushing up is the pressure of the water on the bottom pushing up. So this arrow is pushing up. And then the weight of this column of water is pushing down. And then the air pressure from outside is also pushing down. And they're balanced. So, because I told you at the very beginning that it wasn't moving. So we have the weight going down plus the air pressure times the surface area of the column. And those two together are negative, and when you add them together, they must be equal and opposite to the pressure of the water at the bottom pushing up multiplied by the cross-sectional area of the cylinder. Hey, that ain't bad that I got all that out. That's a lot of words. So let's see here. Let me see if I can do a little derivation for you off the top of my head. So our picture looked something like this. We had a beaker. And we were taking just like this little column of water, like this. That's the water because I can't draw, but whatever. So there's the water, and that's the depth that we got down here. And we have air the air from outside is pressing down on our column of water, and it is exerting a pressure, P naught, or P sub 0. I'm going to call it P naught because that's what I learned how to do when I was a young man. So P naught, the pressure from outside multiplied by the cross-sectional area of this column. That's how much force is getting exerted down. And then we got some force being exerted up, and that's the pressure of the liquid. So that's not P naught, that's just P. The pressure of the liquid exerted upwards. And then the sideways stuff cancels out, so I'm not even going to mess with it. And then you have another thing that's going downwards. Let's see, that would be mg, where m is the mass of the water column. So this column of water has some mass, mg. And they all have to equal each other. So this one is up. And that's got to be equal to, well, I guess there's another way to put it. You could say they sum to 0. So 0 is equal to, and PA is positive, and then these are negative. That's one way to do it. That's not the way your book does it, but it makes sense to me. Your book does it this way, like solves it for PA, so it moves this other stuff to the other side, and you get PA is equal to mg plus P initial, P naught times A. That's the same thing, just rearranged, so it doesn't really matter. But I do have a little trick I got to show you, which you might not have thought of yourself. And I, honestly, I would not have thought of this either, but somebody showed me when I was your age. So the mass of this water column here, the mass of that water, I'm going to come up with an expression for it. So way back earlier when I first started talking to you tonight, I said that mass is equal to the density times the volume, like that. But also the volume of the water column, that's going to be equal to the cross-sectional area of a water column multiplied by the distance of the water column. You see that? How much water is in there? Well, it's the area here multiplied by the distance. You should know this from math class, but I don't know. There's so many things from math class y'all don't know. I sometimes even wonder if y'all even ever took any math, but you're bright kids, so I don't know what the problem is. But definitely math skills often seem to be a challenge. But I can't complain. When I was your age, I had a hard time paying attention to math class, so maybe that's what it is. Anyhow, any kind of shape like this, this is a cylinder. You take the area of one end and you multiply it by how long it is, and then you find out its volume. That's the big idea. I don't know how to say that any plainer. Sorry, I had to drink some water. So it should make sense to you that the volume of water that's in this cylinder should be the cross-sectional area up here at the top multiplied by the distance that it is down to the bottom. That means that the mass of my water must be equal to the density of water multiplied by volume is AD. Oh my goodness, that makes life so much easier because then I can take that and plug it in there. Which means that the density, I'm not the density, the pressure. Why? This is the pressure. This ain't no density. Come on, Mr. Williams. I'm just going to cross it out and pretend I didn't make that mistake. But then it's going to go on a video, and everybody can see it, and they'll know I'm an idiot. But there you go. The density. Oh, my God, I said it again. Ah! It's a good thing I have no shame. So that is not density. That is pressure. The pressure times the cross-sectional area down here at the bottom is going to be equal to, and I'm going to substitute this expression here for mass, which is the density times the cross-sectional area times the depth of your column times G, because I'm plugging this stuff in here for M, so G is still there, plus the atmospheric pressure times the area. Whew! What a pain. Let's be clear. The math steps I did weren't too nasty. I just substituted rho AD for M. And this rho is the rho of water. I'm just going to write that in there, H2O. That's the density of water, and that's a cross-sectional area of your column, and that's the depth of your column, and that's the acceleration due to gravity on whatever planet you're on, which is going to be Earth, folks. Hate to break it to you, but most of y'all are not going to Mars. So we now have the cross-sectional area of that column of water in every term. This is the magic part. Now I can divide everything by that cross-sectional area. Ain't that great? I cross it all out. And I'm going to get the pressure that is experienced at a particular depth is equal to the density of the medium. In this case, it's water. But folks, it doesn't have to be water. I could have filled this up with benzene or air or whatever, but it's not air, only liquids. Benzene, gasoline, milk. I could have filled it up with any kind of liquid, and it would be the density of the liquid times the depth that you are in that liquid times the acceleration due to gravity on whatever planet you're on, Earth, plus the atmospheric pressure outside. And what is so darn cool about this equation is I just proved to you that the cross-sectional area of your column cancels out. So it doesn't matter how big or small your column is. You're going to feel the same exact pressure at any particular depth just based on the depth. That's nuts, man. That's nuts. Doesn't matter how big the container is, how small the container is. It doesn't matter anything. All that matters is the depth. See the depth? Well, these other things generally don't change. The depth, the density of the medium, the acceleration due to gravity on the planet, and the air pressure. But in real life, come on. How often does the air pressure change? Not very. That's not easy to change. You have to go way up in the mountain or way down in a valley, and it hardly changes. And how often does the density change? Well, pretty much it's always water here on Earth. I don't know how many lakes of milk you've jumped into lately, but it doesn't happen a whole lot. The acceleration due to gravity doesn't change much on this planet, which is awesome for us. So the only real thing that changes is the depth. The rest of these can be treated for most practical purposes pretty much like constants. They aren't, I know. But for practical purposes, the only thing that you, human being that you are going to change is D. If you dive in a swimming pool, the only thing you're changing is D. If you dive in the ocean, the only thing you're changing is D. So for most practical purposes, D is what you change. And that gives you the pressure you experience. You see, it's a direct correspondence. This is a direct, not an inverse relationship. So as you go to a greater and greater depth, you experience a greater and greater pressure. And as the depth gets smaller and smaller, you experience a smaller and smaller pressure. And ain't that just the bee's knees? Okay, this is an important equation. You need to know how to derive it on your own, kind of like I showed you here. I didn't do a full derivation, but what I showed you is good enough. Let's see what else we have to go over. Oh, I should remind you that this pressure is caused by the pull of the gravitational force on the liquid. If you were out in space, there would be no pressure in a body of water. I don't know, if you went out into space with a container full of water. I don't know why you do this, but gosh, I don't know why Elon Musk shot a car into space. So imagine that if Elon Musk got it into his head for whatever wackadoodle reason that he wanted to take a, one of those what do you call them? Those trucks, the semi trucks. What if he took a big old semi truck that like looks like this, except you know how they have like this. I don't even know. You see, it goes down the road and it's got this big old cylinder on the back, and sometimes they put gasoline and stuff and whatever these cylinders are. I saw one the other day that said milk. So imagine Elon Musk shot one of these milk, just the container bit, not the truck, just the milk thing way up into space, and you were stuck inside of it. That would be unpleasant for you. Let's say that you had a scuba gear and all that, so you didn't die. That'd be nice. So there you are, off in the middle of space in the milk truck. I'm liking this story already. So would it matter how far you were down in the milk truck? Now, on planet Earth, it would. The deeper you got in the milk container, the more pressure you'd feel. But if you were way far away from the Earth, if Elon Musk shot you out past Pluto and you were way out there in interstellar space, would it matter how deep you were in the milk? And the answer is no, because G would not be pulling on the milk, so then you wouldn't be experiencing any extra pressure. Well, that's a silly thought experiment, but at least you see how the variables interact. Think about whatever other silly thing you need to think about so that you understand this equation. Okay, what else do I need to talk to you about? There's a name for this. I forgot to tell it to you. This is called the hydrostatic pressure. Hydrostatic. Hydrostatic pressure. Hydro means liquid, and static means unmoving. So this is unmoving liquid pressure. If it's not liquid, you can't use this. Folks, do not try to use this equation on your AP exam for a gas. I've seen this happen before. Don't do that. This is not for gases. This is for liquid. And do not use it for liquids that are moving. There's other stuff for that. We're going to talk about it. This is hydrostatic pressure. This is for finding the pressure of a gas that is not moving. Okay, let's look at this picture on the bottom of page 402 in your book. There's a couple important things here. Hydrostatic pressure of a liquid depends only on the depth and the pressure at the surface. There is a principle. It says that that water always finds its own level. And the reason is, if there was some kind of pressure difference, it would equalize. If there was extra water above this level, like it is in this picture, then this extra weight would exert a net downwards force on this side and a net upwards force on this side. So this liquid would move up and this liquid would move down until they were in equilibrium. And then if this tried to keep going up, there would be a net downwards force on this side, and then and it would push this back up. Everything's going to be in equilibrium, no matter how oddly shaped the container. And you will get AP questions like that on your test. You may have some oddly shaped pictures, but the liquid is always going to go to the same level. A connected liquid in hydrostatic equilibrium rises to the same height in all open regions of the container. Now, that is not true if it's got a closed region. Like if you put a stopper here, then it would stay like that for other reasons. Because you wouldn't be able, the air wouldn't be able to flow in. But if the container is open to the air everywhere, it's going to be equal level everywhere. Okay, let's look at this one. This says, in hydrostatic equilibrium, the pressure is the same at all points on a horizontal line through a connected liquid of a single kind. So even the kids have trouble with this. You see how it looks like there's more water above this point than there is above this point? Because there's a whole bunch of liquid all over here, and there's not nearly as much in here. There's more volume here. There's not as much here. So you might think that this is getting pushed on harder than this is, and that would be wrong. That's absolutely wrong. The only thing that matters from our equation is the depth. And they are both the same depth below the surface of the liquid. How much water is above this point? All of this and all of this. So this and this is pressing down on it. How much liquid is above this? All of this and all of this. This is the weird thing about liquids. They experience pressure from all directions. So at this point, it's getting pushed on from here and here and here and here and here, and that pressure is coming from over here too. The total mass above the point is pressing down on the point. All right. The last thing I need to talk to you about is Pascal's principle. Pascal's principle. We talked about Blaise Pascal. We talked about him last chapter. He has a principle about hydrostatics that if the pressure at one point of an incompressible fluid is changed, the pressure at every other point in the fluid changes by the same amount. Okay, that's all I had for you today. I think, I guess not. We've got atmospheric pressure. Let's talk about that. So atmospheric pressure, we mentioned this earlier. I like this little diagram, this little figure down here. You can see that air molecules are quite compressed near the surface of the Earth, and they spread out more and more as you go in an imaginary column into space. So the air's density and pressure are greatest at the Earth's surface. Because of gravity, the density and pressure decrease with increasing height, and the density and pressure approach zero in outer space. Now, gas is not a liquid. Gas is compressible, and that's why this happens. You get compressed air near the bottom of the column and not compressed air near the top. If we lived on a water planet, this would not be happening. I don't think there's anything else new here. I've already told you standard atmosphere and pressure. 1 atmosphere is 101,300 pascals. We talked about that. We talked about what a pascal was. Yeah, I don't see anything else in here that I need to talk with you about. Let's give you a homework assignment. This will be due tomorrow. This is your homework for AP Physics 2, page 427. Let's give you number 8, 11, and 13. Those 3 questions are due when I see you on Wednesday. Thank you for your attention. Have a wonderful afternoon, or I guess rest of your morning and then afternoon. All right, bye kids. See you tomorrow.